Welcome to the last lesson on applications of integration. We are going to look at the last method for finding the volume of solid, and it's called the cross-section method. So we're going to expand upon the basic ideas behind the disk and washer methods to deal with volumes of solids with other known cross-sections. So a cross-section is a three-dimensional figure and the intersection of that plane and that figure. It would be like cutting your object and looking at where you just cut. So when using your disk method, the cross-sections of the solid are circles, like this picture over here. So these are our cross-sections. And if we want to find the volume, we just need to find the area of the circle and substituting the radius into the area of the circle formula. Then we want to multiply it by dx or dy to get the volume of that one slice, and then we'll integrate over a interval. So the definition of volume through integration is if we integrate the area over a to b, and that's where the solid is going to lie in between, then we'll find the volume. So let's look at a few examples first just to give us the idea. We want to find an expression for the volume of the following slices. So if we just look at our area of the face, we know that a square has area side times side, or in other words, side squared. So if I'm given that this is x, that means my height also has to be x, my length. So if I'm looking for the area of this slice, that is going to be a squared for just the face. But if I want to find the volume, I'm going to multiply it by its width as well, which is dx. And this is what we would use for our cross-sections method to find the volume of the entire shape over some interval. Let's look at another example. Let's say a slice is a semicircle. Well, we know the area of a circle is pi r squared. I can replace r with diameter divided by 2 because the radius is half the diameter. So if I'm looking at the one face here, I know the area then will be pi over 2. We replace d with x because that's what it says in the picture for the diameter. And I'm going to bring the 2 in, so this is x squared, and then 2 squared is 4. So it'll be pi x squared over 8. So the volume of the slice then is going to be the area multiplied by the width, which is dx. So if you want to know the other shapes as well, for a triangle it'd be a half times base times height. Your rectangle's length times width. An equilateral triangle is the root 3 over 4 s squared. So let's actually apply this to finding the volume of a solid using cross sections. In example 3, we want to find the volume of a solid bounded by y equals x, y equals negative x, and x equals 4, and we're given the picture. The cross sections are perpendicular to the x-axis as squares. So we're going to look at then the area of a square. And we're going to take a slice of it from our graph. So I know that square should have the same length and height, that these should be the same. The width will be dx. So we also know the square, the area of the square is s squared. We want to find the area of this one face. So if I think about the height, it is determined by the x and the negative x. So what we can do is we could add our length here plus our length here. And of course we want this to be positive. You don't want to do x plus negative x, because then that would be 0. It wouldn't make any sense. We wouldn't have a square anymore. So we just want the length from here to here is going to be x. And the length here to here is also going to be x. So we only care about its length. So overall, the height from the top here to the bottom here has to do with x plus x. Okay, and because the height is 2x, that means the length is also 2x, because this is a square, it has to have the same. And if I look at the overall area now, that's 2x times 2x, which is 4x squared. Then the volume of the slice then is going to be 4x squared times dx, which is our width. So overall volume of the solid is going to be our bounds of x from 0 to 4, the volume of the slice, which is 4x squared dx. And you can put this into your TI 84, 83 to calculate this, which is 85.333. In example 4, we're given the graph, and we're bounded by x equals root x, x equals 9, and our cross sections are now going to be semicircles. So the semicircle, if we go back to a previous example, which is example 2, we found that the area would be pi over 8 d squared. So what we need to find is d. I'm going to draw a semicircle, a slice of it, and let's think about this. If I want to determine the diameter, I want to look at something like this, going across, or I could look at it this way, where the one section here would be the radius and both sections would give me the diameter. With the equation that's given to us, this can actually give us our d, because this whole thing is determined by the root of x. So then, if d is the root of x, I can replace d with the root of x here, and I'm left with pi over 8x. Then the volume of our solid is going to be from our lower x value to the highest x value from 0 to 9 of our area, which is pi over 8x, multiplied by the width, which is dx. We can use our calculator to help us with this. And this is going to be 159 point. It's going to be 15.904. Example 5, we want to find the volume of the solid whose base is bounded by y equals x plus 1, y equals x squared minus 1, and our cross sections are perpendicular to the x-axis. For A, we're looking for a rectangle that is twice the base. So here's the slice we are looking at. That is our width. If we know the base, then we're also going to know the height, or vice versa, because the height has to be twice the base. Now let's take a look at our picture on the very right hand side. Y equals x plus 1 is here, and y equals x squared minus 1 is there. So if I'm looking for the height, this is going to be determined by top minus bottom, which is x plus 1 minus x squared minus 1. And that is going to be the base. And if we want to know the height, it's going to be twice as that. Now think about the area of the slice. It's going to be length times width, which is x plus 1 minus x squared minus 1. We can multiply all this by 2 because that is from our h, and then square this x plus 1 minus x squared minus 1. Then the volume is from -1 to 2, our most left x value to the most right x value. Then our area that we just found, multiplied by the width. This is going to be about 16.2. Let's just say that we have equilateral triangles now. And if you look from above, after example 2, you can find the area of an equilateral triangle. If we had root 3 over 4, the side squared. Okay, so if we know the length of one of the sides, and we know the length of all the sides, because all the sides to the equilateral triangle are the same. It's going to be the same sort of thing as the rectangles, where we have top minus bottom. So then our area is going to be root 3 over 4. S is x plus 1 minus x squared minus 1. Then the volume is going to be from -1 to 2, our most left right point, our most left x point, and our most right x point. Then the area that we just found multiplied by the width, which is dx. This is about 3.507. Lastly, we have the isosceles right triangle, which looks something like this. And these are the same. So one of our lengths is going to be the top minus bottom again, but they have to be the same. So these two here are the same. The width is still dx there. To calculate this area, it's going to be base times height divided by 2. So we're going to do base and height are the same, x plus 1 minus x squared minus 1. I'm just going to square it because they're the same, divide this by 2. So then your volume, our most left x point, most right x point, and then our area that we just found, multiplied by the width, which is dx. Again, using your calculator, this will give us 4.05. For example 6, we're given a region in the first quadrant bounded by the x-axis and the graphs ln x and 5 minus x. So this is your ln x. This is 5 minus x. To find the area, we need to break this into two sections right here, because we have one that is the ln x value is higher than our x-axis, and then our equation changes to 5 minus x, and that's higher than our x-axis. You could also do this all in terms of y if you wanted to, and then it would be 5 minus x minus ln x, the most right minus most left. You can do that as well. Should give you the same answer. But in order for us to even figure out those two sections, we do need to find our coordinates for the intersection point. So what you can do is you can graph this into Desmos or into your graphing calculator and find that intersection point. And once you do, this is 3.693, 3.066. I'm just going to do this in terms of x. Again, you could do this in terms of y if you wanted to. Should give you the same answer. So our most left x point will be 1 up to our intersection, which is 3.693. Our top function is ln x. We could subtract 0, which is our x-axis. But we don't need to include that, because if you add 0, it doesn't change a thing. Then for the next part, I'm going to go from 3.693, which is the x value of our intersection point, all the way to the end, and we end at 5. Our top function is 5 minus x here, and then our lower one is 0, because that is our x-axis, but I don't need to include that. Then we can use our calculator to help us calculate this, which is 2.986. Now we want to find the region R, and our cross-section is going to be a square. You're just going to write, but do not evaluate an expression to help us find the volume of the solid. Okay. So for a cross-section is a square. We know the area of a square is s squared. So we just need to find s. Now s is going to be different depending on where we are. From 0 to 3.693, our side is going to be determined by ln x. And beyond 3.693 to 5, we're going to rely on 5 minus x to find our side. Okay, so that's what we're going to do. We're going to do it into two parts. So from 0 to 3.693, our side for that first portion is going to be ln x, and then to find the area, we square it, multiplied by the width. And the other section, 3.693, we're going to 5, and then to find the side, it'll be 5 minus x, again square it to find the area, multiplied by dx to find the width. And we don't need to do this calculation, we just need to set it up. For part C, we're going to look at a semicircle now. So a semicircle is going to be pi over 8d squared. Drawing a quick picture of this. Because we have two sections, we could probably do this in x, but it's going to be more complicated. It's probably easier for us to do this in terms of y, so we can look at the most right minus the most left. But if I'm doing it in terms of y, I do have to rewrite my equations so they are in y. So y equals ln x. If I take the e of both sides, we're going to get x is equal to e to the y. Now, I have to do the same thing for y equals 5 minus x. I'm going to have to move things around. So this would be 5 minus y. So our most right is going to be 5 minus y. Minus our most left, which is e to the y. That is our diameter. So the volume is going to be pi over 8. Our bounds are going to be from our smallest y value to the highest y value, which is 0 to 3.066. The area, and I can replace d with the diameter I found, which is 5 minus y minus e to the y, multiplied by dy for the width, and then that's it. Then for d, the horizontal line y equals k divides r into two regions of equal area, right? But do not solve an equation involving one or more integrals whose solution gives us the value k. So there's more than one way to do this. I can just give you one. So it doesn't say where we're going to stop or start for here. So this k can be anywhere at all. It's easier to just focus on one section. So I'm just going to cut it off and say here, this is going to be, one is going to be where we start, and we're going to end at the intersection at 3.693. Now this value of k can lie anywhere in here. So we can say that from 0 to k, and if we want to find the volume of just this section, it's going to be what we just found in C, 5 minus y minus e to the y dy. And this should be equal to, because I'm cutting it somewhere in between this interval, it says that these two regions have to be equal. The area has to be equal. Then so from K to our intersection point of the same thing, because we're looking at only that one specific portion, that these would have to be the same, because we're cutting that portion into two pieces where they have equal area.